in which the famous formula that is now considered passé appears. And I wrote to the editors of Science Magazine and I said, did you guys notice? Go look at a modern textbook. Nobody says m0 over the square root of 1 minus v squared over c squared. We don't do that anymore, and they ignored me. So it's practitioners of our age. Dennis is younger than me, but he was probably educated with the old style of teaching. Practitioners are still doing this, and so it's going to take a generation or so to fix this.
I had a question.
Oh, sorry.
There were a couple of textbooks that got it right. Even
Yeah.
before open.
Yeah, can we, I'm reluctant to do this, but Bob, can we go back?
Oh, yeah, this one. Yeah. Hello.
Oh, yes, Dave Murrow has correctly pointed out, yeah, there's some outliers here, and there's some outliers here. And I've highlighted these. This one, this is really interesting. This is a book by a guy who worked at CERN, the accelerator center in Europe. His whole book, the book is called Relativistic Kinematics, and it's all about collisions between particles. And it was really, it's intriguing for me to go back and look at that again now, because if you look at the old books where they calculate that the mass must increase with velocity, it's always done by looking at a collision between particles in two different frames. One of them is that somebody back there throws a ping pong ball, and I'm holding a ping pong ball still, and they collide, and we have to conserve momentum in this frame. And then they do it where the ball that I have and this whole room rushes at the ball that they threw, and the collision occurs in a different frame. And by manipulating those equations, you get the mass increasing with velocity, which is not what happens. It's actually the momentum that changes. This guy never talks about mass. It virtually does not appear in his whole book in Relativistic Kinematics. Everything's about momentum. So he got it right. PSSC, this is the sort of like accelerated physics for high school students, I think. They got it right, and I think, if I recall correctly, they're very explicit about, hey kids, mass does not change with velocity, even though the professors that you might encounter need to be re-educated. So yeah, I'm glad you brought that up there. Oh, and Tipler, there are two Tiplers. One's a philosopher and one's a physics book writer, and Tipler invested a whole paragraph back in 1969 to explain that all his colleagues were getting it wrong.
When did PSSC first start?
Oh, I had it. I had it in 60, I graduated from high school in 62, and PSSC physics existed then.
I graduated in 68, but I missed it.
The interesting thing was, well, anyway, let's go on. So, good question. There were some outliers in both directions. There's still a few books around, and I'm not, when I say a few books around that teach, or modern books, published in the last 5 years, say, that are teaching it incorrectly, mostly they are books without equations. Now, I'm trying not to be a snob, but if you're going to do relativity, you kind of sort of have to embrace the mechanics of it and look at the equations. So you can find modern books published in the last 5 years that mention that mass increases with velocity. But let's keep going. I mentioned Marion, and here's a little precursor of something else we're going to talk about that is still taught in a way that is probably wrong. Rotation of objects that are going at relativistic speeds. We'll talk about that. Okay, I think we're talking about it now. Did we miss a title page? Maybe that's what happened. I'm a little disoriented because I think we've left the issue of mass, and now we're going to talk about something else. And everybody was taught the Lorentz contraction, and it's still taught now. It's taught that if this stick is flying through the room at relativistic velocity, and you measure the length of the stick, it won't look this long. It'll look smaller in proportion to the square root of 1 minus v squared over c squared. Marion has a little paragraph in quoting a very insightful paper done back in the early 60s saying, hey, that's not true, because if you take a cube and throw it through this room at the right velocity, the cube essentially gets out of the way the corners that you can't see and reveals those corners that the light can get to you, which means it appears rotated. If you can see the back corner, the one farthest from you, then the whole thing looks rotated. So, and it's very common to see this statement that a sphere going through your frame at a relativistic speed is not a sphere, but looks more like not a football, a rugby ball, sort of crushed down. So let's go next. And there's lots of discussion about this, including famous people like Roger Penrose. So, here's the sphere, and here's what we were always taught, that the Lorentz contraction would make the thing appear smaller in the dimension of velocity. But there's a little drawing in Marion where they show, well, if a cube flies through your frame, it really looks like this. If your eye is down here looking upward, in the old style of teaching, if your eye is down here looking upward, you just see a shortened cube. But in reality, it looks more like this. This is interesting too, because Marion's book has been in publication, in editions of it, for coming on 40 years. He would introduce this idea very early on, back in 1963. Here's another explanation. The Lorentz contraction tells us what the length of the object will be measured to be. The appearance is another matter. This kind of confuses me, since presumably you can build a machine that allows you to measure things. So he has this, imagines this building flying through your frame, and what I'm trying to say is when this building, and these of course are the windows, when it goes through, you can actually see this wall. And I'll show you some simulations in a little bit where that's demonstrated. Yes?
What direction is the building moving through?
To the right.
Thank you.
So this is well, never mind. Who's right? Okay, so now here's a big long statement by Mills in his book on relativity and quantum physics, which suggests a clarifying statement, but I find it a little bit confusing. Incidentally, I'm Ed Friedman. If you want a copy of this lecture and the references, just send me an email and I'll send you that.
So the good Dr. Van Cleef, who's from Cornell and therefore a literalist, wants to read all of this.
Okay.
Let me
Where's
hold up that grade, I'll ask.
Yeah, where we can,
Pleasure.
okay, let's,
See, Rich and I are working on relativistic rocket dynamics, so we want to get it right. But we can
yeah, Ball, listen,
Right.
Ball cannot get this wrong. Our reputation will be harmed forever. Let's go on. Okay, so here, once again, I'm listing the books. Some of these are famous, like Halliday and Resnick. Some are more obscure. These are the ones that talk about rotation and contraction, but the point is they mention rotation as the source of this apparent shortening. And the interesting thing is, if you work through the equations, and you think about that building that flew through, the short dimension has the length of the Lorentz contraction. But you can see the hidden wall, which that was never revealed to us when I was a student.
And what's your understanding of why it is? Or?
Well, I'm going to show you.
Okay, good.
Well, here's an example. This was a simulation done by people who work at the big Japanese accelerator. And they did, this is actually part of a motion picture. I have stills here. We have motion pictures later, so I hope somebody brought popcorn. But here's what they are saying, that a particle looking down their accelerator sees these nodes in the accelerator where voltages are reversing and so forth. And so at zero velocity, you see a rectilinear array in front of you. At half the speed of light, things have changed a little bit, not much. Well, for example, you see this sort of separation between these two items has changed and been contracted a little bit, but there's no apparent rotation yet. This is only half the speed of light. Now, we go to the next page. Now we're at 95% of the speed of light, and I think you can see that there's sort of, everything is curved. See that bar, for example, which is a straight line at lower velocity, or appeared to be, now has a profound curvature to it, and at 99% of the speed of light, everything is curved. There's rotation going on in front of you because you can see parts of the obscured objects, because as you go by them, the corners move out of the way and let the light reach your eye. Now, this approach, by the way, also resolves a conundrum that most students were confronted with when they took a relativity class. And let me sort of back up, because I have to, for those who didn't take relativity, here's the issue. If I have something pass through my frame at high speed, the older theory was, the object just got shorter as it passed through. But we can turn the problem around and say, if this whole room passed through a frame, we would get shorter, and things in that other observing frame wouldn't. Here's a way to test this. Suppose we take one of these tables and we cut a slit in it that's exactly the same length as this stick, plus a tiny amount. And we have somebody go over to downtown Boulder with a high-speed accelerator, project this thing at us at 99% of the speed of light. So in the old way of thinking, this stick would get dramatically smaller and pass through the slit in the table. I mean, obviously got to have a little bit of an angle, but it would pass through the slit in the table with no problem. But from the point of view of the person standing in downtown Boulder, just as easily could say, well, we'll accelerate the whole Earth in the direction of downtown Boulder, and now the slit in the table gets dramatically shorter, and I got this big stick, and oh my God, here comes the table. And the outcome must be the same. All observers have to witness the same outcome. And if there's going to be a collision between the stick and the table, we both have to observe a collision. We may see it at different times because of relativistic effects, but in one case the stick passes through the slit, in the other case there's a collision. And how can that be? And the resolution is the stick rotates. And so here's a book by from a website, sorry, not a book. This actually is a very rich website worth visiting if you're interested in this topic, from Jose Woodka, who's a professor at Riverside, where he's doing exactly this problem. He has a hole in a table and an astronaut, and he demonstrates that this dilemma is resolved because there's rotation involved. Another famous implementation of this is the outhouse and the pole vaulter. That's famous.
Sounds like a bachelor to me.
I think Don actually is familiar with this, but he's forgotten. Old enough that. So in this other case, the pole vaulter has a big stick, and he's running at an outhouse, which is a tiny building, and if he's going fast enough, the pole is thought to be smaller, shorter, in the direction of his velocity, and he can get into the outhouse, and the door can close behind him with no problem. But if the outhouse is coming at him, he has a big long stick, and the outhouse is now crushed down to the thickness of a piece of paper, and the stick would penetrate the back wall of the outhouse. So how can that be? We have different outcomes, and the answer is the faster you go, the more rotation you get. And it all works out okay. And a great place to look at this is in Taylor and Wheeler's book, Space-Time Physics, where they have lots of neat examples. Let's go on. Here's another example from Woodka of a teapot going by at high speed. And you see it appears to rotate. It's hard to see here. This drawing is not real good. But what it shows, if you look at the website, it's a little better, that the teapot actually rotates. It doesn't crush down in one dimension. It just rotates. So let's skip this, Bob, and go to, this is the third part of the lecture, and has to do with where energy comes from in fission. Oh, stop. Here's a database that I generated at the bookstore and the library at MIT with different books published in different years. So if you get a copy of the lecture from me, you can take a look. You probably own some of these because these are widely used. Even Feynman's lecture series on physics is in here somewhere. Yeah, here it is. And he's a mass dilator
But he doesn't care what you think.
No, he doesn't anymore. But his professor, John Wheeler, is still alive and has done great things to help solve this problem. So let's jump to the movies. I'm going to help you navigate. So kill this.
Why don't you just come to this?
Oh, okay. So a little interlude while I do this, and we will. Yeah, Bob.
Yeah, right, well, there was this guy.
The rabbi and priest was texting while
Oh, wait a minute.
You're all
We're going to be okay. Now, indulge me for a minute because some of these names confuse me, and these are files I got from a website in Australia where they did a bunch of these animations. Now, let me make this big enough. No, there's no roadkill. Doggone. This is.
This is where a guy owns a cat.
This is. Hang on. Cute. Okay, so what we're looking at here is, well, it's pretty obvious. A road, a sign on the left side, a building on the right side. Now, the resolution here isn't fabulous, but you get an idea of what's going on. This is the Newton part of the film. That is, this is low velocity. You go down the road, the sign goes past. Notice there are clouds. Keep that in mind because something interesting will happen. And here's the building on the right, and it's going by, and there's just nothing extraordinary here. This is sort of just to set the stage. Now, let's go to a different film. This one is going to increase the velocity of the traveler dramatically during the film. And that's why the speed of light is up in the right-hand corner. And there's also, they've added this little feature, which is a top view. Here you are, going down the road, and there's a kind of a little smudge over here. That's the building. So I'm going to sit here and I'm going to stop this. So here we go. 20% of the speed of light. Doesn't look too different. We keep going. Now notice the sky. As you're watching this, what's above you is now moving into a place in front of you. There's rotation going on around you. And this also has Doppler shift in it, by the way. Now look at the sign on the left. Can you see that the signpost is curved? And here comes the building, and I wish the resolution was better, but let me just tell, it's hard to see, but let me try to explain it. There was a wall here that you were seeing approaching you. That wall has now rotated, and you can't see the wall. You can see this corner, and you can see parts of the building that were obscured at low speed have now rotated into view, but the part that you're about to pass, and they try to capture that here from a top view, the part you're about to pass is no longer visible. The part you're about to pass is no longer visible. So it's coming to you, but it's rotated out of the way, and you can't see that anymore, but you can see obscured parts of what would otherwise be, and all the light is in front of you. This must be like what happens when you die. All the light is in front of you. There's actually, it turns out in this movie, the sun is above you when the movie starts and rotates. Everything rotates in front of you. And if you're going fast enough, all you see is a pinpoint of light in front of you, which is interesting for interstellar travelers who, people imagine this all the time. We'll accelerate our spacecraft to 99% of the speed of light, and we'll go long distances, but you won't be able to steer. Because everything that's around you, the entire sphere of experience around you, will appear as a point in the distance.
It's the vanishing point. The one you never get to.
So if there's an asteroid out there with your name on it, you won't be able to steer around it. Okay, so let me jump in there. And where's the other one? Ah, get out of the way.
You hear that? Eat.
Yeah. Okay, And then finally, this is similar to, I think this is the same as the Doppler one, but they don't make the colors change, which keeps it a little more clarity here. But once again, as the signpost approaches, you'll see it start bending over, like right there. You can see it's curved. And here comes the building, and the building, it's hard to see, but it has rotated. The face you're approaching has rotated, and you can see around the corners. In fact, right here, this is worth mentioning, this is a corner, the distant corner of the building. As you're approaching the building, it's the corner farthest from you. That's this. But now we're going 95% of the speed of light. We can see the wall that, for normal travelers, is completely obscured. So these animations show that there, in fact, there is rotation. Just like the stills I showed, what do particles see when they're traveling inside of an accelerator? They see everything rotate around them. There are other animations in here that are referenced in the presentation. So if you're interested in getting your own copies, you can use QuickTime to show these films. They are FLC films, not a commonly used film format for me, but QuickTime, modern versions of QuickTime will play this. So I think I'm done. We have time for a few questions that I will not be able to answer. And
Okay,
thank you for your time.
Let's start with Rich.
Yes.
Okay, the old classic thing is if you're in a room and you can't see out, you don't know, there's no way of telling how fast you're going.
Yes.
But it seems that the difference between your ability to accelerate in the direction you're traveling and perpendicular could develop a sensor that would work inside the closed room that would let you know not only that you're moving, but how fast you're going.
That's right. A good point. I have not ever seen that discussed as a mechanism for characterizing your own inertial condition.
Oh, relativistic speedometer. But if it is developed, Draper Labs will develop it.
But the question is, would you measure what Rich is saying in the frame that you're in where you're moving that fast? Or do those effects only appear in the frame external to that where, well, you just stop there?
But you can't know. I mean, it's relativity. You can't know that you're moving if you're in a sealed room, so it has to be what you're saying.
Yeah.
No, but the
That's
point
the
is,
paradox.
you can make measurements in the room that should tell you that you're moving.
Yeah.
But you won't see that in the room, you'll see
Oh.
that from out of the room.
Not
Yeah.
true, because the things differ in the frame.
Another question up here on the front table. Dennis, did you have one or somebody on the front table?
Yeah, well, the pictures from the accelerator were interesting. I was thinking about, if people had been thinking about this incorrectly, as I asked you earlier, that there might have been some sort of engineering implications. And the high-speed particle accelerators was the obvious thing that came to mind. If you were thinking about this wrong, because they do accelerate particles up to 99% of the speed of light. And accelerators do work. So they weren't
Yeah.
thinking about it too wrong, or unless there were some oddities in the design that didn't match the...
No, and the interesting thing, Dennis, is that there are rooms of people like this at places like the Stanford Linear Accelerator, where everybody in the room knows this.
Yeah.
Because they've dealt with the cube of the root. And the reason I say that is, if you work at a linear accelerator, the velocity and force of the particles you're accelerating are parallel. So your ability to accelerate an object to relativistic speed in a linear accelerator isn't the television experiment that I referred to. You're pushing on the back end of the particle, trying to make it go faster, and people who try to do that quickly discover, hey, we got to work really hard because the inertia increases as the cube of that parameter, sometimes called gamma. So that's why I believe that Hagedorn, who wrote a book on relativistic kinematics in the early 60s, got it right, because he was an accelerator guy. He worked at CERN, he was involved in collisions of particles in big accelerators, and those guys know, we know how much energy it takes to run the accelerator, and it's not described by 1 over the square root of 1 minus v squared over c squared. There's a cube in there. And sure enough, that's what the equations say for force and acceleration, force and velocity that are parallel at high speeds.
want a question from the back. Anybody back there got a question?
Greg
Back row,
Kopp.
back row.
Yeah, you had those two different versions of the movie accelerating down the road. One of which you said was Doppler, but why doesn't that make everything in front of you very, very blue shifted and the things off to the side that are actually behind you very red shifted?
Yeah, I don't know. I wonder about what Greg asked about is the Doppler shift movie where the colors were changing as we went faster and faster, why we didn't see everything in front of us turn blue, and those things behind us, which were now receding from us, turn red. I don't know. And now, unfortunately, the website where I got the films is an abandoned website at the Australian National University, so I don't know who created it. But the films have been there for a long time. They've been there about 10 years. And incidentally, there are other films like these out there where students have been challenged in class or whatever to build an animation of what you see when you're traveling at relativistic speed past commonly recognizable objects like cubes and spheres, and they all show rotation. That's not what I was taught. I was taught everything just gets collapsed, it gets shorter, and the stick will go through the table, but the table won't go around the stick.
So I got a question. It's actually a two-part question. The first part's actually not a question, it's a statement. So I got a statement and then a question. It goes like this. If I take the movie, where everything goes in the front, and I take it to the limit that I'm at the speed of light, which means I am a photon. And let's say I'm coming from some galaxy far, far away, like a billion light years away. From us, we look at it, if you were Dennis and you were doing ultraviolet spectroscopy, you would say, okay, it's traveled a billion light years across space-time to get here, to get to my telescope. From the point of view of the rest frame of the photon, though, it's been created and destroyed in the same instant and traveled across an infinitely thin universe in no time.
Mm-hmm.
And now it runs into my Michelson-Morley interferometer. What does it mean to have, or the two-slit experiment?
Yeah.
How can you have separation of slits and all the quantum that goes with it at the speed of light? I mean, there's no
Well,
separation.
yeah, Bob's right. I mean, we don't know what life is like at the speed of light, except that it sort of in the limit, it seems like things traveling at the speed of light don't experience any passage of time.
Right.
And then suddenly there's blackness. It's just like life here on Earth. You live for a short time, things happen, they go whizzing by you, and then you don't have any experience at all. I don't know. I don't know what life is like as a photon. That's it. But I recommend for people who are interested in understanding the beginnings of understanding of this, there's a great book by Feynman. It's a little tiny book. It's called QED. Like 110 pages, and it's not technical, but you will learn more reading that book than you'll learn reading any other science book. It's about how light interacts with material, and it's shockingly it's full of shockingly surprising things. Like, why does glass reflect a few percent, 3 or 4% of the light that strikes glass bounces back? And the intriguing thing is, Newton worried about this problem long ago, and he had a theory, and it was almost right, and others have worked on this, but the real answer is elegantly intriguing. I recommend that book very highly, and it gets to this issue of what is going on when a photon arrives at a physical thing and disappears. What has happened? Somebody.
QED?
QED by Richard Feynman. Now don't buy the other book called Quantum Electrodynamics, which is thicker and is impenetrable. There's a great picture. There's a great picture that was taken in Feynman's study after he died of two ghetto kids holding the Quantum Electrodynamics book and, trying to read it, and it's intriguing. I mean, maybe they were getting somewhere. I couldn't read it, but the little book called QED is just terrific. It's out in paperback. It's about $10. The best science investment you can make. Somebody else.
Ira's got it.
Yeah. Is the limiting velocity of the speed of light an assumption or an implication of relativity?
Well, I think it's really both. If you say the speed of light is limited to, there's a value, and it's the same in all rest frames, you get relativity from that. Right, once you make that assumption, you get a series of results that have all been confirmed.
I see.
There's no refutation of relativity that, if somebody has one, raise your hand.
Einstein took it as a starting